Okay, this is problem 9-20. It's on page 498. I'll read it to begin. During a picnic on a hot summer day, all the cold drinks disappeared quickly, and the only available drinks were those at the ambient temperature of 25 degrees Celsius. In an effort to cool a 335 milliliter drink in a can, which is 12.5 centimeters high and has a diameter of 6.5 centimeters, the person grabs the can and starts shaking it in the iced water of the chest at 0 degrees Celsius. The temperature of the drink can be assumed to be uniform at all times, and the heat transfer coefficient between the iced water and the aluminum can is 170 watts per square meter per degree Celsius. Using the properties of water for the drink, estimate how long it will take for the canned drink to cool to 8 degrees Celsius. Well, we certainly wouldn't have that problem today. You could just set your drink out tonight, and in the morning it'd be nice and cool, ready to go. But summer will be here soon, so let's pretend that summer's on its way and that it's almost here. So here's the iced bath. It's some sort of chest, probably, just an ice chest. And there's water and ice apparently in equilibrium, and so the temperature of the water and the ice are 0 degrees Celsius. What symbol should I use for that temperature? T infinity, good. Hope you guys don't get tired of me asking these things. I ask you this to keep you engaged, and so that hopefully when I give you a question on an exam or a homework, you recognize what all this stuff is and how to put it together. Okay, so this is 0 degrees Celsius, that's right. So that's the temperature of the fluid that's doing the cooling of the can. Now here's the can. Now the person is shaking the can vigorously. Do you think the person's interested in how long it'll take to cool down the can? I would be. I'd want to know how long do I have to keep my hand in this cold water. It's not going to be comfortable. Okay, so here's the can. It's being shaken. I'll indicate that with arrows. And the 170 watts per square meter per degree Celsius, what symbol should we be? Which symbol should we give that? And what does it mean?
That was a K in here.
Not the K. The K is a thermal conductivity. You'll have units of watts per meter per degree Celsius. When it's per meter squared, what is it?
H.
It's H, which is the convective heat transfer. It's basically how quickly the convection heat transfer is going to take place. It's basically what it is, right? It's one of the main parameters. Okay, so H. Now, what is H a property of? You could look at it as a property of the fluid. Really, it's a property of the geometry of whatever solid it is that's being cooled and the fluid and how the fluid's flowing around it. If the person was not shaking the can in the water, would you expect H to be more or less than 170? Less, right? Because shaking is going to increase convection. It's going to increase the motion. The more molecules of the fluid are going to come in contact with the can and transfer heat with it. Yeah, so the convective heat transfer coefficient H is the 170 watts per square meter per degree Celsius. It's supposed to be an M squared times degrees Celsius. Now, the can begins at a temperature Ti of 25 degrees Celsius, and we want to drink it when it comes down to a final temperature of 8 degrees Celsius. Okay, so we could also say that this is the temperature at some particular time. Now we don't know this time yet, right? But this is the temperature we're interested in. So however much time it takes to get to that temperature, that's what we'd like to know. Now the volume of the can or the drink was given as 0.335 liters. And the length of the can, if we were to look at the can, just make a sketch of it, the height of the can, L is 0.125 meters, and the diameter of the can, D, is 0.065 meters. Now, if you go and you calculate the volume of this cylinder, you'll find that it's more than this volume. Now, why the difference between the two? Do you understand what the two things are talking about? Why it's important?
Because there's some air inside there that's not soda?
There's some air that's not soda. We don't care about the air. The air is not going to take much to cool down. It's the liquid that's going to take quite a bit of cooling down. That's what's going to give off most energy. Okay, now, why would we care then about the dimensions of the can? What difference is there? Surface area, that's right. Because that's the surface across which heat transfer is going to take place. And you might say, well, I thought you said some of it is air in the can, and so any heat transfer to that air is not interesting. Well, if we're shaking it around, the fluid's gonna touch all the surfaces, so all the surface will participate in transferring heat. Okay? So we do need the surface area of the can, and what we'll do is just assume that the outside temperature of the surface of that can is uniform. Okay, now the drink is approximately water. Kind of surprising, isn't it? I was talking about this with my daughter the other day, trying to convince her of various truths about the world in which we live that she probably wouldn't be exposed to except for the fact that I'm a geek. I said, yeah, most drinks are actually water. She said, yeah, even milk. I was like, yeah, you're right, even milk. You know, so trying to convince her of all these things. So anyway, water is the main component in the drink, and the properties are pretty close to the properties of water. So the density is about 998.5 kilograms per cubic meter, and I don't believe your author gave that to us. Let me read quickly. Yeah, using the properties of water for the drink. Where did I get this from? Well, what you can do, if you go to the saturated tables in the back of your book, you can look up the specific volume of water at 25 degrees Celsius. If you do that and you take the inverse of it, you'll get the density. So that's probably where I got it from. I don't recall. I didn't make a note of it on my sheet here. The heat capacity, I looked up in another part of the book, and the appendices also give you the heat capacity of water as a function of temperature, and I just approximated it as 4,187 joules per kilogram per degree Celsius. I should have written down a page number, I didn't. I'd suggest you guys try and find them, because it'd be good things to know. You need to know where those things are in your appendices, and then probably put a tab there. The thermal conductivity K of the water is 0.595, and that would have units of watts per meter per degree Celsius. So now we've got all the properties of the water and of the problem set up. Now, how would you model this? What would you do with it? How would you decide how to model it? Because the temperature is going to decrease over time, right? Would you assume that the water inside of the can is all at the same temperature or not?
I thought it said it was. I thought it said it was uniform.
They probably did. Should you? You're shaking it, there you go. Okay, so you're mixing it up. So yeah, it should be uniform, right? So if it's a uniform temperature, then what model should we use? Should we use the really difficult models? Remember the sphere and the plane wall and the cylinder? Or should we push the easy button, right?
Yeah.
Okay, how do we push the easy button? What model do we use?
Lump sum analysis.
Lump sum parameter, there you go. Okay. Lump sum analysis.
Yeah.
So if it's uniform, then the lumped parameter analysis says that the difference between the temperature at some time t and the fluid temperature divided by the initial temperature less the fluid temperature. In other words, the difference right now versus the initial difference ratio is e to the negative bt. Now what we're really interested in is the amount of time required to cool the drink down, because we know we're not going to drink the drink until it has a difference of 8 degrees Celsius, right? Because the water is at 0, so there's a 10. We know it begins at a difference of 25 degrees Celsius. So we're not going to drink it until whatever point in time that the temperature reaches 8 degrees. So let's solve for that time from the equation. When you do that, we did this last time as well. When you do it, you get the natural logarithm of that dimensionless temperature, which is really what this left-hand side is. Okay, divided by negative b. So we need to calculate the parameter b. I'll do it over here because I'm running out of space over there. B is HA over rho V CP. Now how much area does the can have? Notice we need it here. And should I use the area of the can or the area of the liquid? What do you think?
Use the area of the can.
Use the area of the can because that's the area for heat transfer. How about the volume? Should I use the volume of the can or the volume of the liquid? That's a little more difficult, isn't it? In my solution, I use the volume of the drink itself.
Because we care about the drink's temperature, not the whole.
Right. Now, you could make a good case for saying, well, heat transfer is occurring across a surface that is the area we're gonna come up with. In fact, let's go ahead and write that down. It's just 2 pi d squared over 4 plus pi dl. Basically, this here, pi d squared over 4, that's the area of one end. We've got 2 ends, so there's 2 of them. Pi dl, that's the side surface. So there's the area. You could make a good argument to say, well, you should use the volume of the entire can because the object over which heat transfer is taking place has that much volume. So the characteristic length should be based on the geometry of the object, not on the volume of the drink. The volume of the drink would tell you how much mass has to be cooled, but it doesn't say anything really about the heat transfer. Okay, so I actually am thinking that the volume of the drink that I used here is wrong. I should have used the volume of the can. So let's correct my solution and use the volume of the can because I think that makes more sense. Because understand, what we're really trying to get here is a characteristic length. We need a volume per area. And that characteristic length has a lot more to do with the geometry of the can than the quantity of the liquid. Okay, that makes sense? All right. So let's calculate the volume of the can. I'll need some calculator help here. By the way, if you plug in all the numbers for the area, you get an area, let's see, of about 0.0322 square meters. Now let's get the volume of that can. How would we do that? Well, we just need the area of an end multiplied by the height. Right, so that would be pi d squared over 4 multiplied by L. So pi d is 0.065 meters. That has to be squared, divided by 4, multiplied by the height, 0.125 meters. And what do you get for the volume then? I'm off the video, I apologize to those of you watching the video. So the volume of the can is how much?
This is 5.28 to the negative 4th power. Yeah.
Cubic meters? Okay, so 5.28 times 10 to the negative 4th cubic meters. Now, if we were to convert that to liters, we just move the decimal place over 3 places, right? And it would be 5 times 10 to the negative 1st liters. So it'd be 0.528 liters. Make sense? So we got gypped in this can. Either that or some of it leaked out. I don't know which. They sold us a whole lot of air in this can. Well, anyway, that's the volume I think we should actually use. So the B parameter we're going to get here will be slightly different than what I have in my notes. Anyway, let's use the convective heat transfer coefficient, 170 watts per square meter per degree Celsius, times the area. And the area will be 0.0322 square meters divided by the density, 998.5 kilograms per cubic meter, multiplied by volume. Now if we use this volume instead, 5.28 times 10 to the negative 4th cubic meters. And then the heat capacity I have here is in joules, but it may be beneficial to write in kilojoules. Yep. No, we've got watts here, and a watt is a joule per second. So I guess I'll leave this in joules. 4,187 joules per kilogram per degree Celsius. Okay, so let's see what goes away. The joules go away. The meters squared are gone. Degrees Celsius cancel. Kilograms cancel. Cubic meters cancel. And it looks like we're left with inverse seconds, which is what we wanted. Yes?
I got, for the volume, I got 4.14 times 10 to the negative 4th.
You have 4.14 instead of 5.28. Anyone agree with that? Need a second on 4.14 or 5.28, either one up here.
Well, I think for the record.
As long as you guys learn, it doesn't really matter.
4.147 e to the negative 4th.
Yes.
Thanks. Okay, so let's let's use that instead for a volume down here. They didn't sell us quite as much air as I'd claimed. Better write them an apology letter now, I guess.
I have to read that for.
Now, if you look at this, we haven't really been told what this B parameter is. We'd really have to go back to the derivation to understand, should we use a volume like this or the volume of the drink itself? Okay, so why don't we do that since we're talking about it? Let's go back to the presentation, see what lumped parameter analysis was all about. Basically, the idea behind lumped parameter analysis was if the body could be assumed to be a uniform temperature, then there would be heat transfer to that body that would be proportional to the temperature difference between the body and the surrounding fluid. Of course, the temperature of that body would decrease over time. And so we used an energy balance that basically said, well, if you know the mass of the body that's being cooled times its heat capacity, then you can calculate the amount of heat transfer to the body. And then we just basically used an energy balance to set the amount of heat transfer to the body during a small amount of time equal to the change in the temperature of that body during that small amount of time. And the volume was introduced here, where we needed the mass. So it was the density multiplied by the volume to get mass. And that's where the rho V came from. So really this rho V is talking about the mass of the drink. So I was wrong. I should not have used 4.14. I should have used the volume of the drink itself, which is 3.35 times 10 to the negative fourth cubic meters. Okay, so I had to go back to the derivation to remember how that should be. So let's try that instead. You guys understand why I have to use that? Because I'm interested in the mass that's being cooled, not the characteristics of the geometry. All right, so if you plug that in for B, you'd get about 3.91 or so times 10 to the negative 3 seconds. So there's the number for B that we need. So now we've got this piece. So the amount of time required to cool down the drink would be the natural logarithm. We want 8 degrees less 0 divided by initial temperature 25 degrees less 0 divided by negative 3.91 times 10 to the negative third inverse seconds. Plug all of that into your calculator. Now I actually used more precision in B when I went through my solution, and I came up with 291.
Is that 8 or 2 over 25?
I'm sorry, this is 8 over 25.
Okay.
Yeah, it's from the difference in temperature final between the drink and the surrounding liquid. Okay, so as I said, I used more precision than this for my B parameter, and I came up with 291.5 seconds, which is about 4.86 minutes. So would you want to spend 5 minutes with your hand down in ice water, swishing it around? Probably not. You're probably going to find something to hold the can with and move it around. All right. Now let's perform an analysis to see if this was valid. Remember, we should be able to use the Biot number. I need that thermal conductivity that I almost erased. K equals 0.595. There we go. Why don't we check? Why don't we calculate the Biot number? Remember, the Biot number is not the B number. These are two very different things. Okay, the Biot number is a ratio of convective and conductive resistance. Okay. So we need to use H V over A divided by K. Now, this V over A, what are we talking about? Well, we're talking about the difference in resistance of conduction versus convection. So this time what I'm going to use is the entire volume of the can, assuming that liquid is touching all the inside surfaces of the can. Okay? So if I do that, V over A, let's simplify it just a little bit. You could plug in the numbers, but let's go through the math. V is pi d squared over 4L, right, from here. And then A is 2 pi d squared over 4 plus pi dl. Now you can go through a whole lot of manipulation in algebra, and here's what you'll come up with. It's actually pretty interesting to do this. You'll come up with 1 over 2 over L plus 4 over D in its simplest form. I'd like for you to try that. I know a lot of our students are good at algebra and a lot of our students are not good at algebra. So this would be an excellent practice for you. Notice quickly that the pi easily goes away, and at least one of the diameters go away. And so this is not too difficult to get to. Anyway, 1 over 2 over, now L is 0.125 meters, plus 4 over D, the diameter of the can, is 0.065 meters. You plug all that in, you find that V over A is approximately 0.0129 meters. There's the characteristic length dimension of the can. Okay, and that will go in right here. L sub C is the characteristic length. And by the way, this is a V, this is an L. Okay. So now all we have to do is plug in H over K, which is 170 watts per square meter per degree Celsius, divided by K, which is 0.595 watts per meter per degree Celsius, and then multiply by the characteristic length. So the characteristic length we just found, 0.0129 meters. And that should give us a Biot number. Now let's see, the watts go away, the degrees Celsius go away, and we would have meters squared over meters squared. So this in fact is a dimensionless Biot number. When you plug it all in, you get about 3.69, and it is non-dimensional. Wait a second, I thought the criterion for using lumped parameter analysis was that the Biot number has to be less than a tenth or so. What's going on here?
This is a different Biot number.
Different Biot number, well that's possible. You're saying there could be a different characteristic length like we observed in the other models? Is that what you're saying?
No, I thought there were two forms of the B number.
The B or the Biot number? The B number and the Biot number are not related to each other, except they both deal with properties in the problem. The Biot number can be calculated a couple different ways depending on what characteristic length you take. Okay, this is actually the correct Biot number, but it has an assumption built into it that's not right.
Can we use diameter as the length?
Diameter is the length,
Yeah.
as the characteristic length? No, it doesn't have anything to do with the characteristic length. We have the correct characteristic length.
It's because it's being mixed, right?
It's because it's being mixed, that's right. The thermal conductivity K is not a valid way of calculating the resistance within the liquid. Right? There's another way of saying what we've already said just at the beginning of the problem. The thermal conductivity K is the thermal conductivity if the water was sitting still. But the drink water inside is not sitting still. It's being sloshed around, right? So its resistance to heat transfer is much, much lower than what this value would suggest. And so the Biot number is much lower than what our calculation here would suggest. Okay? Same thing as saying if you go swimming in the summertime and you go down to the bottom of the pool, it's usually fairly cool. Turns out that unless there's convective currents or something mixing the water on the bottom will be colder than the water on the top, because the upper water is warmed by the sun, but the water is just not all that great at conducting heat. And so the water at the bottom can be a significantly different temperature than the water at the top. Okay? All right. Any other questions?